Welcome to Virtual Humans, Lecture 6.1, Fitting Simple to Images with Optimization. In the previous lecture, we've seen how to fit models into point clouds in order to obtain correspondences or track humans from point clouds. For example, like this would enable like tracking people from input coming from a depth camera. Or for example, like this would allow us to animate scans by fitting the model to the scans and then controlling their shape and pose using the underlying body model. So all of this is very useful. And it's true that point clouds are a very common input that we might find because it's the output of many computer vision algorithms. It's typically an intermediate output. But if we want to be more general, we should be able to estimate the body shape and pose from single images. Most content in the web is still 2D images. We take lots of pictures. There's lots of pictures in the internet. And many times intelligent systems and robots are equipped only with single cameras. So it's also important that we are able to solve this problem. How do we infer human pose and shape from a single image? We will see this is a much harder problem. So the goal here is, given an image of a person where we do not know anything about the scene, we do not know the camera, we need to estimate the body shape and the pose of the human in 3D. So this, in some way, allows us to see people in 3D. It allows us to understand the scene because if we know the pose and shape of people, we are somewhat understanding what people are doing in the scene, at least at some level. So classically, like there's been two approaches. So historically, there's been two approaches to this problem. The first is using discriminative models. So essentially, you train a model that, given pixels at the input, is capable of producing like a 3D surface of the human or the parameters of the human. Like this, this is a direct learned mapping that you could learn using training data. We will see some of that in the next lecture. The other approach is like the generative approach, where you have a body model and you attempt to explain the image evidence by fitting or optimizing the model parameters in order to explain the image evidence. And this is going to be the focus of this lecture, on this generative approach to estimating human pose and shape from images. So first of all, let's convince ourselves that this is a really hard problem. So first of all, like the human has many degrees of freedom. The pose is a very complex space. You have a high dimensional space, but the manifold of valid poses basically it's just a subset of these combinations of parameters. The types of variations are huge because you can have different skin color, different clothing, different backgrounds, different scenarios, different poses, different interactions. And so this makes the estimation very hard. So also another problem is that now we do not have a point cloud of the person. We have like just pixels, and pixels we saw that is basically a linear projection, right? Linear perspective of the 3D world into an image. So we are losing depth. And because we're losing depth, we have basically 1/3 of the degrees of freedom at least are not directly observable. So this is very well illustrated by this video, which illustrates that essentially you can have many configurations of 3D poses in 3D that project to the almost exact same 2D projection. So let me play this. So on the left, you see the projection of the model, and on the right, you see the different 3D poses. And notice that the projection barely changes while the 3D drastically changes. And this is because you have this depth ambiguity that there's multiple poses that project to the same exact image. And this makes the problem really, really hard. So when we have a hard problem, we need to leverage priors because there's not enough image observations, there's not enough evidence in order to estimate the pose and shape. But we know that humans have a fixed skeletal structure. We know that there's only certain types of poses that are plausible. We know that the motion is mostly articulated. We know that the human shape is roughly symmetric and lives in a subspace. So what can we do to leverage this information? Well, we need a body model. I hope by this, like all of you immediately thought about this. So I showed in the very first lecture that people use those sorts of body models, and it's interesting to see the progression of body models over the years. And so we had body models that were based on a collection of parts, which were based on like some geometric primitives. People like extended these body models to 3D using ellipsoids or superquadrics or Gaussian blobs, and then basically attach a kinematic chain to these models, and then they would track people in images using these models. Many times this required building one body model per subject. So for example, like these are some of the works, including some works that I did during my PhD thesis, which required scanning the person, inserting a skeleton typically manually, and then basically using an algorithm to rig the mesh so that you could articulate it. And this was a very lengthy process and not very scalable because every time you had a different model for a different subject. So you could not even like very easily leverage, and transfer poses from one subject to another. You could to some extent, but it was not a uniform model. And nowadays, all this has been replaced by the simple model, which is, you could say, is a de facto model for human pose and shape estimation from images. All right, so let's look at the problem formulation. We have an input RGB image, that's the input, and we want to estimate the model parameters. And if you're using simple, this means the pose, the shape, and optionally the camera parameters. The camera means like the pose of the camera relative to the human body. So a few years back, let's say about 10 years back when I started my PhD, people were formulating this like probabilistically. So they pose the problem as a problem of map inference or estimating the maximum a posteriori of the model parameters, right? In this case, theta and beta, given the image evidence. This is like the input observation, for example, like an RGB image. And you turn this problem into a likelihood times a prior. So the likelihood is basically this explaining like the image. So essentially you want to measure how likely the image observations are given some model parameters X. And then you have some prior, for example, on the shape of the person or the plausible poses. And this is something that you can learn or construct before you have seen the image evidence. So how do you model this likelihood in these generative models? I should have mentioned the discriminative models, they basically learn a mapping directly from image to X. And the generative models like essentially try to maximize this likelihood times the prior. In this lecture, we're going to focus on generative models. And the question is how to model this likelihood. How do you model the probability of, or this posterior, how do you model the probability of model parameters given image? So there's two main approaches. So one is using optimization. And essentially this is equivalent to finding the map estimate of the posterior, right? The maximal posterior estimate. And the other approach is to not use optimization, but use basically you could say like Bayesian optimization, where you approximate the posterior with weighted samples. So you have a bunch of hypotheses for the parameters X, and every hypothesis is like weighted by a number that determines how likely this pose is. Nowadays, almost nobody uses this approach because for high dimensional spaces, you need a lot of samples and this is not very efficient. Although maybe these models could be revisited now with the power of with GPUs and so on. But nowadays, most approaches for this generative approach, they typically rely on optimization. So let's look at how this is done. And you will see that they decompose the posterior as a likelihood times a prior. So the general framework typically involves these 3 steps. So one is extracting features from the image. Then is predicting these features with the model. So here, the feature is a silhouette of the image. And here in yellow, I'm showing this silhouette predicted by the model, which can be obtained by projecting the model into the image and rendering this silhouette. And then basically you would find correspondences or matches between the image observation, in this case, this black silhouette, and the silhouette of the model, in this case, this yellow silhouette. And then basically you would optimize the model parameters in order to make these residual errors, these individual contributions here, as small as possible. Right? So you have like extract features, predict and match, which is finding correspondences, and finally optimize. So there's some key questions like, what are good features for fitting? So let's look at this first. So people have used all sorts of features like silhouettes, distance transforms, edges, shift, appearance, rendering losses. In the end, what you should consider is that any feature that can be predicted from the model efficiently and is fast to compute and potentially like is differentiable, then this is a good feature for optimization. So for example, let's look at the distance transform. So one thing you can do is to compute a distance transform of the silhouette of the person that you're seeing in the image. And then basically you maximize the overlap between the distance transform of the image and the distance transform produced by the model. And so here, for example, this is a bidirectional matching of distance transforms, which in one case, it's pushing the model inside the silhouette, and the other is forcing the model to explain the image. Yeah. So the number 2 is like this more like what we've said many times, that it's better to optimize this data to model terms rather than model to data. But we've also seen that combinations of both typically lead to better results. Okay, so that's the process. You extract features and then you predict these features with the model, and then you try to align those features. Now, to align those features, you need to match, you need to know which features correspond to what, right? We have an ICP problem, like similar to this registration of 3D shapes. So how do you do this? Well, like you could generalize this ICP algorithm for matching to images. You basically extract features, you project the model to predict those features with the model, and then find matches, you optimize, and you iterate this process, right? Once you have better model estimate, you can project again, and so on. If you want to learn more about like model pose estimation beyond this lecture, you can check this book chapter, which is called Model-Based Pose Estimation, which I wrote in 2011, but the key ingredients and concepts haven't changed so much over the years. So, right, so there's a question here for you, is like how to match like the 3D simple model with the 2D image. So check your understanding. How should we match? Should we match the model to the image or the image to the model? And think about this question. Think about questions like, for example, what if the images contain a partial body? What would happen if I would minimize a model to image term? Yeah, so think about this, and we will discuss these questions in the Q&A session. And also think about what would happen if features contain outliers. So we saw in the assignments that optimization can be quite susceptible to outliers, especially if we're using like a loss that is based on L2, right? So we have seen that outliers can dominate the optimization. So, okay, so what objective do we actually optimize? We want to match the predicted features with the features in the image, but what does the objective look like? So it turns out that a lot of problems can be formulated as a non-linear least squares problem. So we have here a total error. This is a scalar, okay, which depends on the model parameters. And we want this scalar to be as small as possible, right? Ideally 0. So this will be a sum of individual contributions, EI, for each of the features. For example, a feature could be edges, or it could be like point-to-point matches or point-to-line distances. You know, these are these individual contributions. At this point, these EIs are these individual contributions, which are also scalars, okay? And so this can be written as a sum of squares errors. So you have here from I equal 1 to n, like the difference between the predicted 2D image feature given by the model, right? That's why it depends on xt, minus the observed 2D features in the image, right? This could be like, for example, like 2D key points, or it could be edges, or it could be silhouettes, or whatever, right? And you have like this norm here, because this is like, this is measured in the image plane. So these are typically like 2D dimensional, but it could be like other dimensions if you're measuring different things, yeah? And you have like this norm here squared. And that's why it's called a nonlinear least squares, because you have a sum of squares error, but this Ri of xt can be a nonlinear function. And it is a nonlinear function because it depends on the body model, it depends on the projection operation, which we've already seen that is nonlinear, and so on. Just to remind you, like this formulation, it's good to like give it like a probabilistic interpretation to know where things come from. So if you assume that the errors are independent and Gaussian distributed, this least squares problem is equivalent to a map estimate or to an ML maximum likelihood estimate if you don't have the prior. So here, like if you have the posterior probability of parameters xt conditioned on the image yt, this can be turned into like the likelihood times the prior. And if you write the likelihood as this exponential of the sum of individual errors, right? We notice that when we take the minus log of this, like this term here will be equivalent to this term over there, right? And why can we put all this summation inside the exponential? Because we are assuming independence. Because we assume independence, we're going to have like a product of exponentials, which will turn into an exponential of the sum, right? So because we made this assumption, we can plug everything together into a single estimate, into a single exponent. This is an assumption. In practice, the errors are not independent, because like if basically they are driven by they might not be independent. So one thing to notice here is that they are conditionally dependent on the pose. So given that I know the pose, then the errors are conditionally dependent. Anyways, maybe that's not so relevant for this lecture, but it's important to know like where these things come from. All right, so So here we have like a little bit more in detail, like what is actually being optimized and how do we optimize. So you can write this sum of square errors as the dot product of two vector error vectors, which are of dimension 2n if the features are two-dimensional. For example, we're measuring like the distance of 2D key points, or we're measuring the distance between two silhouettes. We would have like this vector, this error of residuals, this vector of residuals, E, and basically this scalar error would be obtained as a dot product of E, so as a dot product of E transpose E, right? And this would give us a scalar. And essentially, what does this error look like? Essentially, this is like a collection of residuals. So for example, like here you have the residual for the first match, and then like you would have the residual for the nth match between the model and the image feature, right? And then you do this dot product, and then essentially you see that, you know, this term multiplies with this term and so on. So this is equal to the sum of squares. All right, so let's look at how do we optimize this. So we have here this dot product of this vector of residuals, E. So when we use math boldface, E means vector of residuals. When it has no math boldface, notice here, no math boldface, it means that it's a scalar. All right, so we have here this vector of residuals, and what we can do is to linearize. We can see what happens if I add a small perturbation on model parameters. And basically, given this small perturbation, we can see, what the perturbation should be in order to make this total error smaller. Okay, so that's the trick. You don't linearize directly the scalar error, you linearize the vector error. Okay, so you have here this vector error, and you consider this vector error evaluated not at xt, but at xt plus delta x. We know that this vector error can be linearized as E plus the Jacobian times the delta x. The Jacobian is the derivatives of E with respect to the parameters, which is a matrix. It's a matrix because this is a vector, right? Okay, so we have E plus Jacobian evaluated at xt times delta x transpose E plus Jacobian evaluated at xt times delta x. So what should we do? Or let's develop this further to see the terms. So essentially we will get 1/2 of E transpose E plus delta xt jt transpose E plus 1/2 of delta xt jtj delta x. So let's look at the terms. The first thing to notice is that E transpose E is the current error. It does not depend on delta x. So for the purposes of finding a good gradient step or a step delta x that minimizes this expression, it's completely irrelevant, right? So this term we can ignore. Then we should observe here, this is a term that has delta x t multiplying this jte. And what we should notice is that jt times the error is the gradient of the scalar error. Okay, don't get confused here. Take some time to digest this. So one thing is the vector error, E math boldface, and the other thing is what we had before, which is this scalar error, which comes from the dot product. If you take the derivative of this, you will see that, I mean, that's the gradient, and this will be equal to jt times E. Yeah, that's exactly jt times E. Yeah. All right, and then basically this is the first term, and the second term, which is a quadratic term, will have like delta x transpose times this matrix jtg times delta x. And you know, by observation, we can see that this jtg is an approximation of the Hessian, right? Again, of this error here, right? So what should the dimension of the Hessian be? for this scalar error? Well, we're taking gradients with respect to xt, so it should be of dimension xt times xt, because it contains the second derivatives, right? So we have to consider all the cross terms. All right, so what we can see now is that we have this term here, and what we can do is take derivatives and equal to 0 in order to obtain the following step direction. Minus jtj, ignore this mu I for a second, inverted, times jte, right? To go from here to here, we're just taking derivatives with respect to delta x and equaling to 0. This equation, I mean, this is basically finding, this is a parabola. This is a parabola, right? Because it has like this, this linear term and this quadratic term. And what we're finding here is this, like the minima of this parameter, of this parabola. Now, why do we add here like this mu times identity? This is essentially to make the this inversion better behaved. So this is what is called, like, without this mu I, this is what is called the Gauss-Newton step. JTJ inverse times JTE, this is what is called the Gauss-Newton step. And if you add the mu I, what you should think is, okay, first of all, what happens if JTJ equals to 0? Or when JTJ is very small relative to mu I, right? So when mu is very high. What happens is that this term is almost negligible. And what really matters is JTE. So we're finding, we're taking a step which is equal to mu times JTE. And we said that JTE is the gradient. So essentially, when mu is very large, we're taking a gradient step, just gradient descent. When mu is not very large, we're taking the Gauss-Newton step. And so this is what you typically do, and this is called Levenberg-Marquardt. You adjust dynamically during optimization this mu parameter to make, depending on whether you're close to the minima or far from the minima, you use different mu parameters to control the optimization. When you're far away from the minima, you typically want to use a large mu in order to have gradient descent, which is safer. When you're getting closer to the minima, you want to use Gauss-Newton because it's quicker, right? The parabola will be a better approximation of the neighborhood. Okay, so then we take a step in this direction. Xt plus 1 equals xt plus delta x, and we can basically iterate this thing. And the nice thing of this algorithm is that it does not require to compute this Hessian involving all these second derivatives. It only requires us to compute the Jacobian matrix, which is a matrix of first order derivatives. All right, so just to emphasize on the same thing, so JTJ is an approximation of the Hessian, mu I times JTE is the gradient of the scalar error that we're minimizing, and JT is the Jacobian of the vector error function, right? Is the derivative of these error residuals with respect to the parameters of the model. So let's look at one example. I mean, there's many papers that follow this principle. I mean, really many papers follow this principle, and not only for human pose and shape estimation, but also for 3D shape estimation and bundle adjustment and whatnot. I picked here one example, which is covariance scaled sampling for monocular 3D body tracking, which I think is really seminal work, which was following this principle, and it showed one of the first trackers that that could differentiate through the model parameters. So here they were using features that were based on motion boundaries, edges, and optic flow. And then basically they had this probabilistic formulation, as I showed before, where you have this exponential and this integral. This is equal to this, like, same as the summation of individual feature contributions and times the prior. And, you know, you take the minus log and you turn this into a sum of squared errors, and you have these terms here. These are like delta R, times delta R transpose. These are these square terms. This matrix here should not scare you. It's just weighting the individual components to add robustness. So this was fairly sophisticated, and it could achieve already quite impressive results. I mean, I think that this was 2001, and so for that time, this was quite remarkable. So, however, although this was really remarkable and it inspired many works, and I recommend you also read some of these earlier papers, this was very constrained to lab settings. It was not very robust to difficult poses and backgrounds. So the natural question is like, okay, so you're saying that the concepts haven't changed that much, but what has changed in the last 20 years? And I would say that there's two key changes or two breakthroughs. And one was that basically now we have like very reliable 2D pose detection methods. These are methods that can automatically detect the joints of people in images quite reliably. And those are based on convolutional neural networks that detect, knees and feet and heads and hands in images. And they've been trained with a lot of data, because data in 2D is easy to annotate. It's easy to collect training samples of images and 2D joints. And so this works quite reliably. For example, like there's methods like OpenPose, which are widely used. And then there's the availability of 3D body models like SMPL that are flexible and easy to use. And they don't require scanning the person and fitting the skeleton and all this tedious process. This is now fully automatized with a 3D body model, which is widely used in academia and industry. And leveraging these two advancements, so people have been able to achieve remarkable accuracy for 3D human pose and shape. This is, for example, the method of Simplify by some colleagues. And so the basic idea is following on the principles that we've shown before, but now we have much better features than people had like 15 years ago. So it's again extracting features, but now the features are 2D joints, which are quite reliable. And then you have like the predicted match. So you basically can project the 3D joints of SMPL into the image. And now going back to this characteristic of features of whether they are differentiable and whether they are easy to predict and easy to compute, well, clearly 2D joints are the easiest feature to compute from a body model. It's just 2D points. You can just project them with a single like matrix multiply. They are naturally differentiable with respect to the model. And so this makes them very easy to use features for optimization, right? And then so basically you minimize an L2 distance between the detections and the predictions of the model. That's the basic idea of Simplify, which is a method that is the baseline still for many human pose and shape estimation methods. So the basic idea is, again, like extracting features using a bottom-up approach and basically matching these features using a top-down approach, making the SMPL model match those 2D key points. So that's the idea. To bottom-up and top-down should match. So you have an energy, which is basically taking parameters shape, pose, and also the camera orientation relative to the body. And basically, like it depends on the estimated 2D joints. And so basically the idea is to minimize this distance and with an objective function that measures this, for example, like the L2 between the predictions and the detections. Now the question is this enough? Well, I was already emphasizing that we have a lot of ambiguities, a lot of difficulties in single image estimation. And this is similar to this video I showed before. You might have a good fit from the viewpoint of the camera, but if you change the viewpoint of the 3D model, you will see that there's weird things happening. For example, like this leg is moving forward in order to fit this image. So what is actually happening here is that this model is too tall for this image, and this is compensated by moving the leg forward and making the leg appear shorter from the frontal view. So, okay, so we can ameliorate some of these ambiguities by using priors on the pose and shape, as what we did for 3D registration. So we can build a pose prior from a data set of human poses, and we can build the shape prior basically from the shape training data set that was built to that was used to build a simple model. And this will lead to these errors that consist of a data term. This is like, in probabilistic terms, this would be the likelihood term and the prior terms. Prior terms on the parameters. So basically you have a prior on the pose and like some prevention of joint angle bending and a prior on the shape. These terms are very, very similar to terms that people had been using before. The only thing is that now the data term is much stronger because of the detections. Now, because of the simple model, like one can optimize for the shape, and this will adapt better to the observations in the image than these models that were based on, for example, like quadrics or cylinders, right? Okay, so there's also further problems, like you can have interpenetrations. There's nothing in the simple model that prevents that. So what you can do is to build like an internal. You could prevent penetrations by using the mesh directly, but this would be computationally very expensive because you would need to find triangle to triangle intersections. And when you have like 13,000 triangles, this is like basically too expensive to compute. So what the Simplify authors did is like to approximate the simple model with some basic, what are called capsules, which approximate the shape of the simple model. And then you can compute intersections between capsules very quickly. And those capsules can also be differentiable. So essentially, this allows you to resolve errors, like, for example, like this intersection that can be resolved after imposing an interpenetration loss. So, so that's how the objective function looks like. You have the data term, and you have like pose priors for the pose and shape, and you have an interpenetration prior as well. And they showed, like, for the first time, really cool results on very challenging images from the lead sports data set. And so basically this showed that you can, leveraging these two breakthroughs, right, these better detection and better body models, you can address like a long-standing problem in computer vision, which is that of estimating pose and shape from images. Of course, when you're working on human pose and shape estimation, it's very important to evaluate your method not only qualitatively, but also quantitatively. And in terms of data sets, things have also changed. So in the past, people were only evaluating their methods based on indoor scenarios, based on data sets like the human EVA or human 3.6M. Nowadays, we have other data sets like 3DPW that include outdoor scenes of people interacting. Actually, this was is a project where I was that I was leading, and this is if you check the data set, you will recognize many parts of Tübingen where we collected this data. So this allows you to evaluate these methods on these more challenging scenarios. And notice that we also provide like reference poses for these challenging images, and this allows to evaluate methods on that. And even more challenging are datasets like COCO and lead sports and so on, where you do not have like the 3D pose annotations because those are basically almost impossible to obtain. So the community is moving towards like addressing more and more challenging scenarios, more and more challenging backgrounds, interactions with multiple people, and so on. Okay, so one thing that Simplify did not address is like being able to capture the full expressivity of humans. And for this, you need to capture also the hands, the face, and the body. And this is what the Simplify X method addresses. So in Simplify X is an extension on Simplify, and it upgrades the simple model to have detailed hands and face, and it updates the priors from using a mixture of Gaussians for the pose to a variational autoencoder, and it also trains a classifier to predict the gender from the image and select the model accordingly. As I was saying in one of the previous lectures, it's a very good idea to build a model for females and another model for males, because the statistics of shape are quite different. And so it makes a lot of sense to predict first which gender the person is and then fit the corresponding model to it. But the key ideas of like model fitting remain essentially the same. So essentially the idea is to add this mano model, which was already trained, and a face model, and basically integrate everything into a joint model, which is called the Simple X. By the way, I think that this angry face that you see here is myself. This is for one of the captures. And these are the things that they make you do in order to capture the full range of expressions. All right, so basically for the pose prior, instead of having a penalty on the poses using a mixture of Gaussians prior, you can train a variational autoencoder, obtain a latent space Z. So for those of you who do not know what a variational autoencoder is, you basically will encode like the poses into a latent space, typically of lower dimension, and then you will have a decoder, and you will train this model to minimize the auto reconstruction error. And then you obtain a latent space Z that represents the pose, and hopefully this latent space behaves more like the manifold of visually plausible poses. And then what you can do is you can optimize directly these latent space parameters instead of the original joint angles of the simple model. So let's see some of these results. So you can see that this can capture better like the expression, for example, like these signs of victory, or like of signs of surprise or tension. And so you can see that by capturing the hands and the face, all this human emotion is much better captured. All right, but there's still lots of limitations of optimization-based methods. So essentially, when the detector fails, of course, these methods also fail because they are based on fitting the model to the detections. Of course, like depth ambiguity can be resolved to some extent with the body model, but it's still, for certain images, it's still very ambiguous. So for example, like here, we have like these two fits that are basically incorrect. Like you notice that the body has been flipped with respect to the image. Or for example, here, the leg is like, further away from the camera. And after fitting, like we obtain a leg that is closer to the camera. And still like this, when you look at the joints, like this leg is essentially fitting the image well. And here do you have like a leg swap because of like ambiguity in the detections. So these are typical failure modes that still happen in optimization-based methods. Sorry. Okay, so the pros and cons of local optimization are that if well implemented, they can be fast, and they are typically accurate provided with a reasonable initialization. And but they are prone to local minima. They require some initialization to work well, and the matching cost is ambiguous. Knowing how to associate image observations to body model predictions is still ambiguous, the same way as ICP was ambiguous. So, like in the next lecture, we will see whether we can use learning to solve or address some of these issues. So we will see this in the next lecture. That's all I wanted to say about fitting models to images and optimizing pose and shape. And thank you very much. Bye-bye.